elementet organizativ që ofron ligji për Akademinë e Shkencave. Ne kemi tashmë një komision të përhershëm në fushën e inxhinierisë. Dhe për kështu praktikojmë edhe krijimin e njësive kërkimore, do të thosha virtuale të përkohshme, që përbëhen nga grupe ekspertësh që punojnë në institucionet e ndryshme dhe që fokusohet në problemet të saktuara. Duke u nisur nga ky koncept, ndoshta profesor Jorgo si kryetari Komisionit të Inxhinierisë mbase mund shikoni dhe mundësinë e një zgjerimi. Me këtë rast. Për të mos u zgjatur, unë ftoj profesor Nejtanin që thot disa fjalë.
Thank you, Frasheri, dear academic Jorga Kachani, dear chairman of Alpcolt, Engineer Arjan Giovanni, dear Dean of Civil Engineering, Faculty of Pristina University, Professor Florim Grachevsky, dear Rector of Poca University, Professor Ahmed Ostaz, distinguished guests, honorable invited lecturers, ladies and gentlemen, dear students, it's my great pleasure to welcome you to the Symposium of Design Codes of Dams and their Seismic Safety in Albania. First, I would like to express acknowledgement and appreciation to the organizing committee for the support and dedication of their time and energy to make this symposium a successful event. Especially my acknowledgement are for the chairman of Alpcolt, Arjan Giovanni, who gave us a lot of support and energy to realize this symposium. I would like to extend a warm welcome to all the academicians, experts, engineers, and students from Albania and Kosovo that are present today. In this symposium, during all the day, will be presented lectures from our distinguished invited professors, engineers involved in the dam design, talented researchers, and young academicians and engineers. This symposium is jointly organized by the Albanian Academy of Science, Civil Engineering Faculty of Polytechnic University of Tirana, and the Albanian National Committee of Large Dams, and it is hosted by the Academy of Science in Tirana, Albania. The symposium is the second to be organized in 2 last years from Academy of Science and Civil Engineering Faculty of Tirana in an excellent collaboration with Commission of Engineering, which has members prominent engineers in the various fields of engineering. Both symposiums are related to earthquakes and design codes for different engineering work. The first one was focused on Eurocodes and the structural safety of the construction works, and the second is related to design codes of dams and their seismic safety. Both symposiums are motivated by recent earthquakes in Albania. Between May and December 2019, Albania has experienced 3 powerful earthquakes in the southeast and central part of the country. The southeast of Albania has hit by several earthquakes at the beginning of June 2019. The second major earthquake hit Albania on 21 September, and the third earthquake occurred on 26 November 2019. In the case of Albania, out of around 60 reported large earthquakes spanning the period of the last 2,000 years, more than half took place in the 19th century. This indicates that the number of strong historic earthquakes affecting Albania may be underestimated. It is almost impossible to prevent an earthquake or seismic event from occurring, but in areas of high seismic risk, it is possible to significantly mitigate against the worst effects on life and property. Improvements and the enforcement of the building code to withstand seismic shocks, reduce the risk of casualties and damage to private and public properties. Through years, civil and hydrotechnical engineers were faced with many changes due to developments in technology and methods of calculation. Albania is close to formal adaptation and use of structural law codes. A part of them are already translated and accepted as Albanian standards. In this context, hydrotechnical engineering community must be properly supported with guidelines that describe the design and construction requirements for the construction of a proposed dam or the reconstruction, modification, enlargement, rehabilitation, alteration, or repair of an existing dam in Albania. These design and construction requirements include the submission, review, and approval of engineering plans and specification, inspection, reports, and records. Dam failures not only put the public at risk, they can also cost our economy billions in damages. Failure includes more than the dam's damage, but can negatively impact many other infrastructure systems, such as roads, bridges, and water systems. When a dam fails, resources must be devoted to the prevention and treatment of public health risks, as well as the resulting structural consequences. Therefore, this symposium is a very good opportunity to provide some information on the design codes of dams and the requirements about their seismic safety. The two symposium sessions will focus on very interesting topics of a great impact on the design codes and the construction materials of large dams, as well as on different experiences on state control of large dams. Dear participants, we all know the importance of investing time and effort in increasing knowledge and developing technologies to improve living standards. The presentation of works in such important fields undoubtedly serve this purpose. The Faculty of Civil Engineering has always had in its objectives the creation of an environment as stimulating as possible for all students, doctoral students, academicians, engineers, and which is characterized by an atmosphere of true intellectual efforts. A great contribution to the preparation of hydrotechnical engineers who have contributed in the design and construction of hydrotechnical works was given by the Department of Hydraulics and Hydrotechnics, created at the end of September 1953, with the name Cátedra Hidráulicas de Termotecnicas, or in English, Chair of Hydraulics and Thermotechnics, as parts of the Faculty of Construction at the time of Higher Polytechnic, as part of Higher Polytechnic Institute. On behalf of the local organizing committee, I would like to thank all the organizations, individuals, and participants for their support and contribution. In the end, it's an honor for me to have this opportunity to convey some thankful words on behalf of my colleagues. I would like to express my sincere appreciation to Albanian Academy of Science, and especially for the President, Academic Skënder Dinushi, for supporting our efforts to make this event happen. My appreciation are also for the advisory committee to Academic Jorga Kachani and Academic Neki Frashëri. It is our honor and privilege to host distinguished lectures whose knowledge and experience that have been acquired made them prominent researchers and engineers in their field of expertise. I would like to give special appreciation to Dr. Michael Bardanis, Professor Nico Koyani, member of it called Claudia Russo, Professor Fabrizio Barpi, and my special friend from Greece, Dr. Georgios Pelokas. I wish you all a great day. Thank you very much.
Faleminderit. Në vazhdim të programit, unë duhet të kërkoj ndjes për mungesën e kryetarit të akademisë. Sot është një ditë në disi e veçantë për akademinë, pasi për herë të parë janë 4 aktivitete në të njëjtën ditë. Dhe vazhdojmë me programin. Ftoj inxhinier Arjan Jovani, kryetari Alkol.
First of all, I want to say thank you very much for all colleagues and participants that are present here. And I will be happy to give you an overview on the dam design and construction in Albania. I want to give the general information for our dams in Albania, because as a lot of you know that we have 350 large dams in our country, and 300 are small dams. So we can say that we have a very big history in this sector, but our duty is to protect them, to monitor them, and to increase their life. From 350 large dams, 10 of them are more than 60 meters. And for the hydropower energy, we use 24 large dams. For irrigation and fishery, 325 large dams, and for drinking water, 2. You can see the first dam in Albania is constructed at 1957, is Ulza Dam. The tallest dam in our country is Fierza Dam with 166.5 meters, and the longest dam is Muriz Dam with 3,480 meters. So you can see that we have constructed the dam that have difficult to construct, but also we must monitor them and in the future. The types of large dams in Albania are embankment dam, concrete gravity dams, concrete face rockfill dams, roller compact concrete dam, rockfill dam with clay core, and rockfill dam with asphalt concrete diaphragm. And also Bovilla, that is a rockfill dam with geotextile membrane. The operation purpose of our dams are for hydropower production, for irrigation, water supply, transport, flood protection, aquaculture or fishery, solar energy, and tourism and urban development. Here are some graphs to see the number of large dams according to the completion date. And there you can see that from 1990 until now, we have constructed only 8 dams. So mainly of them are constructed before 1990. So this is important for us, why we want to have the focus for the monitoring of the large dams. Also, another graph is according to the district in Albania. And if you will see the map that is outside of them, you can see that 25% of our dam are in the district of Tirana and Durrës. You know that 4 years ago, there also was a strong earthquake there that, for good luck, till now we have not any dam failure in this area. Our legislation that is based for our activity, first of all, is our law number 8681 for the design, construction, operation, and maintenance of large dams, is the law number 45 on civil protection, the decision Council of Ministers for the rules of dam safety, the decision on functioning of alcohol, and decision on structure of Albanian National Committee of Large Dams. Also, 2 years ago was another decision of Council of Ministers for the determination of the procedure and terms to obtain the risk assessment for the subject, which required the construction permission. Also, in our activity, we use the recommendation of ICOLT, because our committee is member of ICOLT from 60 years. Next year, 1964, we was the member of ICOL. This is the structure of our committee. Our committee is government body under the Council of Ministers and support from the Ministry of Infrastructure with technical inspectorate and technical secretariat of this. Here are main duty of Alpcolt: exercise the state control for the safety dams, of dams, organize and approve the preparation of legal and technical documentation in this field, support technical progress in design, construction, operation, and monitoring of dams, promote the large dam sector, approve the project for construction of new dams, as well as the rehabilitation project of the existing large dams, inform the Council of Ministers about the condition of dams and give the opinion on their improvement, and represent the Albanian state in ICOL. Main problems of large dams in Albania are old age of large dams. A lot of them are more than 45-year-old. Increase of urban area below the dams. Old technical standard for design, monitoring, and safety of large dams. Sedimentation process of the reservoir. Lack of maintenance and monitoring of existing dams. Lack of technical audit from independent qualified expert and certification of dam safety. Lack of study for the future of dams and their reservoir. Lack of dam assets evaluation and management, and climate change and environment protection. Main challenge for the future of our sector in Albania: preparation of the new technical standard for design, monitoring, and safety of dams, improvement and update of dam legislation, institutional and organizational reform in dam sector according to the European experience, modern program for maintenance and monitoring of large dams, certification of dam safety, training of new technical staff of large dams for the monitoring and safety. Existing guideline prepared by the Alpcolt during 4 year is a guideline for preparation of dam technical passport, guideline for technical rules on operation, maintenance, monitoring, and control of large dams, guideline for preparation of preparedness plan for civil emergency caused by the activity of dam operator, guideline for control of dams after earthquake, guideline for monitoring of dams, and guideline for decommissioning of large dams. Proposal of Alpcolt for the new standard in the future: technical standard for design and control of earthquake-resistant dams, technical standard for design and monitoring of embankment dam, technical standard for design criteria of calculation and control of flow in spillway of large dams, technical standard for classification of large dams according to their risk, technical standard for solar and floating solar plants on the large dams and their reservoir, and technical standard for monitoring of sediments in the reservoir. This is the briefly information and presentation for the situation of our dams in our country. So I want to say thank you again. And here is a photo from Bovila Dam. Thank you.
Thank you. Dhe tani ftoj kolegët Bapallëku dhe Belokas për të bë moderimin e seancës së parë.
Good morning, everybody. Now we are at the point at which we will start with part one of the special lectures, which is design codes and construction materials of large dams. Together with Markel, we will organize this session. So, concerning the first speaker, Ms. Sarah Lazaridou, there was a very serious personal problem that prohibited her from coming here. So she's very well excused about that. So, unfortunately, we will not have the opportunity to hear her, to see her and hear the interesting things that she would say. So now, we may proceed with the second lecturer, which is Dr. Michael Bardanis, Director of the Laboratory EDAFOS and the President of the Hellenic Society for Soil Mechanics and Geotechnical Engineering. He will deliver a lecture, Benefits of Large-Size Laboratory Testing for the Design of Earth Dams. Michael, please.
Thank you very much, everybody, for being here. First of all, I'll have to excuse myself. I suffered from a cold over the past 4 days. It's not COVID, mind you. I have been testing myself every day since Tuesday. But if the voice starts not to come out very much, please excuse me. Some formal thanks. I have to thank very much for the invitation, the Albanian Academy of Science, the Civil Engineering Faculty of the Polytechnic University of Tirana, and of course the National Committee of Large Dams of Albania. And I also want to thank personally Professor Skodrani for the kind invitation to give this speech here. I was expecting that I would be the second speaker after Sarah Lazaridou, but unfortunately her father died on Monday. Lazaros Lazaridis, a very prominent figure in the design of many dams, especially earth dams in Greece, with a very long history of decades in the design of dams. So I will give my speech today. I know I am in a one-day conference about codes, about seismic design, but I will focus on what is my own expertise and the benefits it has to offer. Now, you obviously know in this room the main parts of an earth dam. You don't need much explanation from me, but the main ones that actually contribute to the strength of an earth dam is the cells, the upstream and downstream cell, and the impermeable core itself. Now, usually the cells are from free draining material, coarse grained material, although on occasion they can also be from weak rocks, weathered rocks, and in that case, especially in the upstream part, we use horizontal drains in order to avoid serious conditions when we have rapid drawdown. And especially when it comes to seismic loading, we suffer from the attenuation of the acceleration due to the seismic loading. We may have an acceleration at the base, which becomes much larger at the crest. So when we are expected to design for the earth dam, we have much more serious loading, earthquake loading, being applied to the specific earth dam. There has been a lot of discussion worldwide about what is the appropriate acceleration to use. Most of the methods used today will do something I will show you in the next slide. However, we have even seen designs that because of the very large acceleration close to the crest, they actually introduce reinforcement like the one we have in reinforced embankments in the cells of the earth dams close to the crest. Now, many methods have evolved which actually take an earth dam, they actually separate it in parts. I have given an example here when you can separate it in 3 parts, and they try to find the representative acceleration when you are performing an an analysis, a slope analysis for each part. So this alleviates the problem because in the past we have seen some very, very large accelerations being applied even when we are doing a slide analysis for the whole dam. So this kind of separation here sort of alleviates the problem and brings into our analysis more representative values of the actual acceleration values that we use in this kind of analysis. However, my main focus is the following. What properties do we consider in the analysis we carry out for earth dams? Many times, we have seen values as low as 35 degrees or 40 degrees, even for free draining cells that we are using in earthquakes. And here I have run an exercise where I have taken an embankment dam. For simplicity, I have taken out the earth core for the impermeable core for a moment. And what I have done is the following. I have tried to find out what should be the minimum inclination when we are performing analysis without seismic loading. If you have assumed at the beginning 35 or 40 degrees, and if the actual angle of shearing resistance was 40, 45, 50 in this particular case, or 45 or 50 in this particular case. And I have calculated the increase that this kind of assumption introduces in the volume of the earth dam. Please notice the figures. If you have assumed a value of 35 degrees, you can expect an increase up to 15, 16% if the actual angle of shearing resistance is 40 degrees for the very high dams. For 45 degrees, up to 40%, and for 50 degrees, even up to an impressive 65%. Therefore, although practically all of us have many times performed assumptions, have used assumptions on the angle of shearing resistance for the material of the cells, there are benefits if we try to attempt to measure, really measure in large size devices, this property here. A little bit of soil mechanics. After all, I'm the president of the Hellenic Society for Soil Mechanics, so yes, you would be expecting some soil mechanics from me. A uniform soil, a soil that practically has a single fraction. A well-graded soil, where you can see all the grain fractions being present, minimizing the voids and maximizing density. A poor graded soil, where some grain fractions are not there in the right proportion. A gap-graded soil, where some fractions are totally missing. And also, the last part of my lecture is going to focus on this, materials where we have gravels and stones, but have also a very large proportion of fine-grained material. And to put this into perspective of actual grain size distribution curves, this is obviously what a fine-grained soil with gravel stones looks like. This is the green one, what a uniform soil looks like. This is what a well-graded soil looks like, and so forth. Plus the effect of sphericity and also the angularity of the grains. Here I have a small picture which shows how the sphericity increases and also how the grain angularity decreases. We can see material like this that we actually obtain from rivers in order to construct our cells, or we can see material like this, very angular, which we are obtaining from quarries in order to construct our cells. And this is one of my beloved devices in the laboratory of Edafos that I direct, a very large direct shear device. It's the largest in Greece. It has a shear box with 45 centimeters diameter and a maximum height of 30 centimeters. It was designed in order to be able to measure properties for very high dams, and this is why the vertical stress that can be applied can reach 3 megapascals. 3 megapascals. And also, this is one of my lovely pictures where we have the comparison of the shear box of the large device with its little cousin here that you can see, the shear box of a conventional device of 60 millimeters in diameter. And you can see that the maximum grains that can actually go into the big cell are practically larger than the sample that we can put in the conventional sear box. This type of machinery needs a lot of infrastructure, large size infrastructure, in order to be able to cope with the various parts, in order to be able to cope with the quantity of materials you want. We are talking about a sample that weighs in the order of 100 to 120 kilos, each sample, plus special care for the porous stones. The porous stones for a small design is something easy that you actually pick off the shelf. But when it comes to design this large, what is a porous stone? A porous stone is something that you actually have to construct yourself from a porous concrete in order to be able to use it in this kind of device. So, first of all, let's look at some results from rounded, free-draining, coarse-grained materials and sand gravel mixtures. These are river materials that we are going to see. Lots of materials from many areas of Greece. These are primarily of limestone origin. I have focused in this lecture on limestones because it's a material that we also find in Albania as much as we find in Greece. And I have some examples in order to be able to relate these grain size distribution curves with the actual material. So here we have a material that is very close to a uniform material, and you can see the maximum grains that can be placed in the device. Here you can see some well-graded materials in the middle, and here you can see a material like this, which has a lot of fines. In this particular case, mind you, these are fines that are non-plastic. And here are the results. Here also to relate with these nice pictures I had before, and here are the results. I'm not going to do any special analysis. Yorgos Belokas is going to present some very cool engineering analysis in the face of Eurocode 7 later on in the afternoon on the same results, but please look at the differences. The minimum value of the angle of shearing resistance measured in all these materials from the whole country was 44 degrees. The minimum whenever. And if you compare to what you would obtain from a conventional shear box device, if you had taken all the coarse grained out, would be in the order of 33 to 37. So try to look at the benefit we can expect here and look at the minimum values. And then if we go to angular free draining coarse grained materials from quarries, again, only limestones this time. Again, I have some pictures in order to be able to relate with the grain size distribution curves. Uniform soils, well-graded soils here and here, soils with many more fines that also come close to sand with gravel. And here I have a typical example because in this case we have used some very high relative density samples in order to measure the shear strength, and you can see how the peak strength develops, and then it falls to the strength after large strain, and you can look for a specific soil, the amount of difference between the peak strength and the strength after the large strain. And again, I will focus in the general view of things. Please again look at the lowest strength even after large strain. Never falls below 43.5 degrees again. And if we go to the peak strength, somebody may argue that I can use it when it comes to seismic loading. It never falls below 50 degrees. And especially because of the non-linearity of the failure envelope that we have in coarse-grained materials, expected because it is like having a rock mass which is very broken, which we would expect non-linearity. So this is something that comes very close to rockfill. You can see that for very low vertical stress, the values are extremely high and much higher than the values we use in common design assumptions. And even if you go to the values after large strain, again, you can see that we have these values of 43.5 degrees, even up to 52. And especially for the low vertical stress, again, due to nonlinearity, even above 45 degrees. So again, there is benefit here to gain from actually measuring and making sure that we keep measuring in the construction of our dams the values of shear strength that we can obtain from these materials. And finally, we often fantasize, I use on purpose the specific word, we often fantasize when we talk about impermeable cores that they are made of pure clay. Well, the reality has shown that this role of the impermeable core has often been fulfilled by weathered or weak rocks, like fleece, a very common material that we can find also in Albania, chalk, weathered gneiss, serpentinite, schist, and whatever weathered rock we can find. Again, this material can be placed in the device with one additional benefit, that exactly because of the size of the device, we can place instruments inside the shear box that will measure the pore pressure that may want to develop along the sliding surface. The problem of the shear box is that quite often we are afraid that what we are measuring is not really drained. And this is a problem we have in the small devices. But if you go big, this big, then you can take off the market a common sensor that we use and we place in actual large dams. This is the kind of sensor we would place in the field. You can place it in this kind of device and know the actual pore pressure that is being developed along the sliding surface. So these materials that we see them in the field and they look rock-like, but once we introduce a couple of wetting dry circles, they actually turn to a fine-grained medium with stones and gravels. We can measure the pore pressure and actually use it in order to interpret the shear strength data that we obtain. And here is the look of it. Weathered schist, weathered serpentinite, weathered gneiss, weathered siltstone fleece, chalk, materials that we normally assume or measure in small size devices, angles of shearing resistance in the order of feet 25, 26, 27, 28, and yet these materials have a much larger angle of shearing resistance, especially combined with a value of cohesion. Therefore, quite often, the strength of both shells and impermeable cores is being underestimated. We are using assumptions, which, yes, they are on the safe side, but they cause the need for larger volumes. And also, when it comes to seismic loading, exactly because it introduces a need for higher strength, we have many more problems, and we have seen even the need for reinforcement close to the strength. The kind of results I have showed you is that if we actually go forth in measuring the properties of these materials, there are a lot of benefits in order to cope both with the seismic loading and the need for lower volumes. Finally, just a little bit of advertising. As the president of the Hellenic Society for Soil Mechanics and Geotechnical Engineering, please try to follow us on LinkedIn. We have many announcements that we make there. And also look up for the channel of HSSMG in YouTube, where we have many recorded lectures from whatever conferences we have, many of them in English, where you can actually hear to them on the YouTube at your own will. Thank you very much for your attention.
Dear Dr. Michael, thank you very much for the presentation. It was really helpful and very nice presentation, so thank you. If it will be, sorry? Yeah. Question? Yeah. Please, no. If there is any question, please provide them. If there is no, I have a question, but mostly related to this acceleration. You mentioned that the acceleration at the top, the crest of the dam, are much higher than in the bottom part. But what about the dumping or this energy dissipation of the dump? Do you have any reference, which is the amount? Because we know that the dam react mostly or wish to react in this elastic range. But anyway, those are material, and due to your experience, even in laboratory, which is the damping, let's say, or energy dissipation, let's say, of this kind of dumps? Do you have any reference value to suggest or to address about this?
For a reference, especially regarding the distribution of acceleration, we can use throughout the height of the dam for a more realistic. I would generally suggest Papadimitriou and Boukouvalas in 2008. I may send it over so that people can use it, which actually show about the attenuation of the acceleration, but also how that can be more representatively distributed along the height of the dam so that you introduce a more representative value depending on the foot of your sliding surface. Because what we have noticed in the past is that people take the highest value of the acceleration that can be found in the crest, and they apply it when they are carrying out a sliding analysis for the whole dam, which is, okay, it's on the safe side,
Yeah.
but it leads to some results that are totally unrealistic. So that one is very helpful. It is in English. I will try and find it and send it over for anybody interested.
Thank you very much. And the comment? Please. No. Please. Now I want to invite my professor, Nico Paiani, for the second presentation, Adoption Seismic Safety Provisions from Other European Countries for Dams in Albania. I want to thank Professor Paiani because he is one of the initiators to start and to go further with this dam safety. So thank you very much, Professor, and please, the floor is yours.
Thank you, Dr. Babaleku. Hello to everyone. Here is the title of the paper I am presenting, prepared through a close collaboration with my colleague, Ricard Luca. First of all, we should present some materials, technical documents that are referred to throughout our presentation. So the references are Romanian Normative Act, referred hereafter as normative. Second, a French technical report, refers hereafter as risk seismic. Third, the new Italian Norme Tecniche, referred hereafter as Norme Tecniche. And the last one, the fourth, an equal bulletin on selecting seismic parameters of large dams, referred hereafter as seismic parameters. We will start this presentation with our opinion, supported by a series of arguments that Albania must improve its rules regarding the seismic design of dams and other hydraulic structures. Hereafter, for simplicity's sake, all these structures will be referred as dams. As known, for other engineering structures, such as buildings and bridges, a few years ago, Albania effectively adopted a series of structural Eurocodes, more specifically Eurocode 8, Design of Structure for Earthquake Resistance. However, dams are not included in Eurocodes. At this point, improving the rules are provisioned for seismic design of dams is necessary, as a considerable amount of time has passed since the last revision. Practically, it occurred 35 years ago. It is now obvious that Albania must reflect as soon as possible the achievements in the field of seismic analysis and design of dams during the last 3 decades. A new engineering code would ensure a safer seismic design as well as a better approach to the rehabilitation of strengthening of existing dams if needed. Given our circumstances, the best way for Albania to achieve this objective would be to adopt and adapt the relevant contemporary provisions prepared in other European countries. In various seismic-prone countries around the world, there are numerous technical documents, rules, and guides concerning this issue. Normative notes that in 2004, the ECOLT European Club has prepared a summary guide collecting such documents from European countries. Other similarly valuable works may have been carried out later, but they have been not available to us. To our knowledge, a unified European standard to cover dam design or even only a seismic standard, as the Eurocodes are, does not exist. At the same time, there is an excellent source that provides useful engineering material on dam safety in all aspects, the International Commission of Large Dams, I called in French Commission Internationale des Grands Barrages, CGB. For a long time, through its bulletin, the ECOLT has been producing regularly publications containing various technical experiences, guides, and recommendations that are very valuable to the hydraulic engineering community. So when preparing, adopting a document with provisions regarding seismic dam design, thousands and thousands of pages provided from ECOLT and other sources throughout the world are available as reference guide. However, in the case of Albania, a country that aims to join the European Union, it would be more appropriate to adopt provisions similar to those prepared in European countries. The rationale is that although dams are not covered by Eurocode 8, which is already in wide use in Albania, it contains some key seismic requirements, no different to those used for dams. Firstly, for all building structure, dams included the seismological design data, magnitudes and seismic acceleration values are taken in principle from the same sources. The maps of the seismic hazard of the country, and if needed, by specific microzonation study. Also, the engineering procedure used to evaluate the stresses and strains, safety factors, and so on, are rather similar, particularly when dams are built of concrete or masonry. In fact, Eurocode 8 is cited in quite a few cases in current documents on the seismic safety of dams in European countries. Of course, there are also many aspects, terms, and analytical and design approaches which are specific to dams and other hydraulic structures. As such, they are reflected in the relevant international and European technical documents provisioned as recommendation. Next, we provide an overview of analytical approach containing the technical document of seismic dam design of select European countries. This is done only in view that this would be useful for some of these approaches could be adopted in the new Albanian provisions. Overview of seismic provision in select European countries. The main seismic documents on which we focus here are the French and Romanian one, risk seismic and normative. Also, in a lesser extent, the new Norme Tecniche d'Italia. Also, some similar documents from other countries too. The French and Romanian documents reflect, of course, the rich experiences of the respective countries, being at the same time, most of them consistent with the ICOLT recommendation. We think that are also in good relation with Eurocode 8. They both contain, apart from their main text, a considerable number of annexes, which may effectively serve to clarify and explain terms and analytical relevant procedures, as well as other helpful information. Very instructive are some SALT examples included therein, where current methods for seismic analysis of different types of dam are used. This is important as while today such analyses are performed using software and computer techniques, which would be used in Albania as well, it is necessary for structural dam designers to know the details of structural seismic calculation of dams, starting from the simplest methods such as pseudo-static method R. Also, rather useful is the inclusion in the annexes of the risk seismic normative of the experiences from other countries. The equal also and distinguished professionals too. Normative contains information regarding the Indian, American, and Canadian seismic provisions. Risk seismic similarly contains aspect and provision from seismic countries such as Austria, Switzerland, Spain, Germany, USA, Canada, etc. Aspects related to the assessment of seismic standard, hazard. The level of seismic hazard shown on the maps of the territory of a country is often called normative level. The Romanian normative stipulates that this is the minimum level to be considered in seismic dam design. And other provision also say like this. The French risks seismic makes this implicit assumption as well. The latter provides details about the new seismic map of France in effect from 2011. The territory of the country is divided in France into 5 zones, from the weakest, the first zone, let's say, up to the strongest, the 5th one. The corresponding peak ground acceleration, PGA values that vary from 4% of G up to 30% of G. These values correspond to the 10% probability of being exceeded in 10 years, in 50 years, corresponding to a return period of 475 years. This is consistent with the use of seismic acceleration maps required by Eurocode 8, and this is consistent with the seismic hazard map expected to be officially approved soon in Albania also. As known in seismic provision, the design seismic acceleration values are affected by the importance of dams to be designed. Risk seismic applies 2 basic criteria for this. Dam height and the reservoir volume of water, to group dams into 4 classes of importance, ranging from the A, most important, to D, least important. The factor increasing the PGA values provided in the map vary from around 1.1 for the D class up to around 2.2 for dams in the A and B class of importance. Apart from using the normative method, that is National Seismic Map, risk seismic normative stipulate conducting when needed specific macroseismic studies around the construction site in order to obtain more reliable data, seismic data. These studies may be done using the probabilistic method and or deterministic one. The main outputs of the last method are, as known, the maximum seismic potential and the reference earthquake. characterized by the respective magnitude M and PGA expected value to be used in the seismic design of dam. According to risk seismic, very important dams should withstand the so-called maximum historical probable earthquake, and in French, the terminology French is assessed by this method. It may be considered similar to the maximum credible earthquake, famous MCE earthquake as per Anglo-Saxon terminology of equal bulletins, which is generally assessed by this method. In this sense, the risk seismic seems to unify the concept of reference earthquake and SNHV earthquake in French terminology. However, sometimes there are 5 or 6 terms familiar to the earthquake engineering professionals to unify concept of reference earthquake. However, sometimes it is the so-called increased safety earthquake that is accepted as a reference earthquake. This is practically done by adding the magnitude with 0.5 or increasing the Mercalli intensity by 1 grade. This provides additional safety to compensate for the relatively short period of historical observation. The normative has a similar interpretation of the MCE earthquake to the risk seismic. The risk seismic stipulate that dams shall resist the following earthquakes, selecting through specific seismological studies by using the probabilistic method. One, a rather strong one, called SAS in French, or they correspond to SEE earthquake in English terminology, safety evaluation earthquake. A moderate one called SBE in French, or OBE in English terminology, operating basis earthquake, must be withstood by the dam. According to the normative, each of the above earthquake types are to be applied to in seismic analysis of dam separately. Regarding the return periods of OBE earthquake, these documents require for it to be not less than 100 years. The importance classification influences considerably the assignment of return period values to be chosen when specific studies are carried out using the probabilistic method. The risk seismic gives the following return period values for the SEE earthquake. This table is very important. Here you see the class of dam, A the highest and D the lowest. And for the A class of dam, the return period according to risk seismic is 5,000 years, and so on for B, C, and D in 500 years. Meanwhile, a value of about 200 years is given in risk seismic for the OBE earthquake. The High Court recommends some very long return period for the SE earthquake in the seismic parameters. In addition, the High Court stipulates that SE ground motion shall be taken as the maximum of the probabilistically and deterministically evaluated ground motion. On the other hand, it is considered appropriate to choose a minimum return period of 145 years for the OBE earthquake. That means 50% probability of not being exceeded or being exceeded, the same. Meanwhile, the risk seismic recommends that the final choice between the probabilistic method and the deterministic method should be left to the project owner. In French, maître d'ouvrage. This decision can be determined by the importance of the structures, etc. In some European countries, the return period of SE earthquake or its equivalent MCE chosen for very important dams vary as follows. Just you can see here some countries, Switzerland, Germany, and Norme Tecniche d'Italia give us return period for the equivalent CE earthquake values that go up to 2,475 years for dams of great importance. But our colleague from Italy will inform maybe much more about this. The return period values accepted in some European countries for the OBE earthquake or its equivalent are as shown in the PowerPoint presentation for the OBE earthquake. Meanwhile, the new Italian Norme Tecniche for an equivalent OBE gives the return period values of 150 and 200 years, depending on the importance of dams. Safety criteria. According to the resisting an SAS in French or SEE in English terminology, earthquake means that the structure must meet the requirement of ultimate limit states, shortly no collapse requirement, or in French, état de non-effondrement de la structure. Whereas for the OB earthquake, it must meet the requirement of serviceability, limit states, so or limitation de dommage. As stipulated in the risk seismic, the safety criteria are in principle not different from those of other built structure provided in the Eurocodes, particularly in Eurocode 8. However, the risk seismic normative, Romanian, also account for the specificity of dams related to the control, verification of stresses, strengths, stability, foundation, and so on. Aspect related to the method of seismic analysis of dams. Both risk seismic normative consider the two kinds of dams, let's say rigid dams, concrete masonry, arch, gravity, batteries, etc., and earth dams. Both documents indicate the ways of structural modeling, linear, non-linear, and use of calculation method from pseudo-static to dynamic. Regarding the latter method, the two documents present particularly the spectral model analysis and the principle of time analysis, history analysis, and direct integration, and so on. Risk seismic also contains some useful simplified dynamic method used in rigid dams, method Newmark, Chopra, Tardieu, etc. Meanwhile, regarding the spectral model analysis, it is worth noting that normative requires that the number of model shape to be considered in that analysis be 10 up to 20 in both concrete and earth dams. Okay. The following figure extracted from a normative concrete dam example solved using the SAP 2000 program show the model based on the finite element method and its first four vibration shape corresponding to the situation full reservoir. Regarding the spectral method, risk seismic provides some seismic spectra fairly like the Eurocode 8 for seismic dam calculation. There, a separate section provides a specification for the reference ground on the soil types to be used in seismic analysis. And regarding the forces acting on a dam during an earthquake, both risk seismic normative and other provision, other rules from other countries dedicate also a section to the seismic hydrodynamic pressure from the water of the reservoir based on the well-known Westergaard and Zangar solution. Risk seismic devotes considerable space to the use of pseudo-static method, a simplified dynamic method in earth dams, as known, the former, example, Bishop method, etc., served for the preliminary assessment of slope stability, and the determination of the critical pseudo-static coefficient Kc, which is starting factor for the latter, more precise method. Meanwhile, regarding the simplified dynamic method, Rishi Smith detailed the ones proposed by several distinguished experts in the field, from Newmark, Chopra, etc. There are also two Greek professors, Boukavalias and Papadimitriou, also in 2003. In addition, it mentions some linear and non-linear elastic and post-elastic dynamic methods. For example, those conceived by Seed and other distinguished professors. Okay, conclusions and recommendations. It is necessary for Albania to improve the seismic design provision for dams and other hydraulic structures. Adopting and adapting seismic rules from the other European countries would be an appropriate approach. To undertake this task, there is a need to form a competent working group of Albanian professionals with good knowledge and work experience in areas such as dam analysis and design, earthquake engineering, and engineering seismology, and dynamic of structures. This group should be tasked with, we think, choosing the models of respective rules to be adopted, or provision, or standard. Albania now has the potential to create such a group or task force. The seismic culture of the Albanian engineering community today is much improved compared to 35 years ago, when the last revision of the Albanian rules occurred. However, undertaking and realizing such a nationally important initiative, let's say, requires the fulfillment of the following prerequisites. One, the relevant Albanian engineering scientific and governmental institution must duly consider support in it in all aspects, as was the case of adoption of Eurocodes and particularly Eurocode 8. Foreign technical assistance should be secured to ensure collaboration and exchange between the Albanian team of professionals and the expert in the field from I called European Club and national competent bodies of relevant European countries. Thank you very much.
Thank you, Professor Pogiani, for this comprehensive overview of the design codes across Europe mainly. So if anybody from the audience wants to make a question, please, this is the moment. It looks like that we do not have any questions, but let me ask you something.
Yeah.
You said about the return period, and there are many choices for selecting the return period. Now, depending on, let's say, the earthquake characteristic and history of each country or the consequences, what would be the criterion to select a representative return period for the design? For the earthquake, I mean.
This is a very difficult question. We just are starting to think about and to show, to consult foreign experienced countries about, because it's a range, a very large range, let's say, of return periods to be taken into account. Of course, first of all, will be the importance of the dam. If a dam of, let's say, 100 meters in height, we will recommend, and now we just recommend for the designers that the return period must be not less than 2,000